Hey guys, we're in lesson 4.3 and this is task 3, multiplying polynomials. All right, model with polynomial multiplication. Amber opened a cell phone repair company in 2000. From 2000 to 2020, the function n of t that models the annual number of cell phone repairs in thousands, and the function c of t that models the average cost of a repair in dollars are shown in the photo. Where t is the number of years since 2000, find a function r of t that models Amber's total annual revenue from cell phone repairs. Then use the function to estimate Amber's total revenue in 2015. All right, so annual number of repairs, n of t is number of repairs, and annual cost per repair, c of t is cost per repair. Find the function r of t, so revenue equals numbers times cost. All right. And that's what it says here. R of t equals numbers times cost. Use the polynomial multiplication to find the product n of t and c of t. All right, so they've used vertical multiplication here. You can use vertical or horizontal. It doesn't matter. But once you multiply the numbers times the cost, that gives you r of t, which is your revenue. So the annual revenue function is listed right here. Note that since n of t is measured in thousands of repairs and c of t is measured in dollars per repair, their product, r of t, gives revenue in thousands of dollars. Estimate the total revenue in 2015. Since 2015 is 15 years after 2000, substitute 15 for t in the equation r of t. So here's r of t, and again, 2015 is 15 years since 2000. If you go back to the original problem here, it does say t is the number of years since 2000. So that came from the original problem. And then it says that once they substitute 15 in and simplify, they get 189.525. So Amber's total revenue in 2015 was about $190,000. All right, so all they did was put this in thousands of dollars because that's what the directions said. It was in thousands of dollars, and they rounded it. So it says it was about $190,000, okay? Then says that since R of 15 is 189.525, Amber's total revenue in 2015 was about 190, not 190,000. Why is Finn incorrect? Select all that apply. All right, so the function r of t, this is the revenue, gives revenue in thousands of dollars. So we did see that. The function r of t gives in 10,000s of dollars. That's not true. 189.525 represents revenue of $189,525, or about $190,000. So that's true. 190 is just the rounded number or the estimate. All right, it says, in what year did Amber's total revenue first exceed $300,000? All right, so we know that years are since the year 2000. So for this one, you're going to take 20 and substitute it into the revenue equation. So right here, instead of 15, we're going to put 20 and then see what that revenue is. Here we're going to use 16 and here we're going to use 17 to find those numbers. And it says, in what year did Amber's total revenue first exceed 300,000? So when you plug those numbers in, when you get the number 300 here, or slightly above 300 because it says to exceed 300,000, we know that 300 point something is going to be represented in thousands of dollars. All right, so I'm going to leave this one for you guys to work. If you have any questions, let me know. We're going to move on to task 4. All right, lesson 4.3, task 4. This is verify and use polynomial identities. A polynomial identity is an equation stating that two polynomials are equivalent. For example, the equation a plus b quantity squared equals a squared plus 2ab plus b squared, showing how to square the sum of two terms is a polynomial identity. One way to verify an identity is to start with one side of the equation and rewrite it until it matches the other side. Another way is to show that both sides of the equation equal a third expression and are therefore equal to each other. All right, verify the polynomial identity. All right, so this is an identity that's important in this class. The one above it, this identity is a sum of a perfect square, and there's a sum and difference of perfect cubes, which is this one right here. Anyways, these are very important on the ACT. So this is something not only important for this class, but these identities can help you answer questions more quickly on the ACT if you understand the identities. All right, so it says to verify the polynomial identity. So here, since the right side of the equation is simplified, simplify the left side. So this side's already as simple as it gets. So we're going to simplify this side. So you're going to take A and multiply it by everything in this trinomial here. And then you're going to take negative B and multiply it by everything here. So you can see they've done the exact same thing here, except they've written it out. So you have A times this polynomial, and then you have negative B times this polynomial. So that's what they did in this first step. Then they have distributed A times each thing inside of here, and then down here they got to where they crossed out like terms. So plus and minus A squared B and a plus and minus AB squared, those cancel, and that's what leaves just the A cubed minus B cubed. All right, it says what property justifies the second step? Okay, so this is distributive property. All right, and it says what property justifies rearranging the terms of the expression. All right, so anytime you rearrange the terms, they're just rearranging them to put them like terms beside of each other. That is commutative property. All right, so it says therefore A minus B times A squared plus AB plus B squared equals A cubed minus B cubed. So again, this is a difference of cubes, something important to know. Also, again up here, this one is something that we'll talk about more, but this is definitely something you need to know as well. Some perfect square trinomials. All right, we are moving on to task 5. All right, we're going to verify and use polynomial identities again. All right, so the polynomial identity, x squared plus y squared, quantity squared, equals x squared minus y squared, quantity squared, plus 2xy squared, can be used to find Pythagorean triples. Verify the identity, then find a Pythagorean triple using x equals 5 and y equals 4. To verify the identity, show that each side simplifies to the same expression. All right, so one thing I want to talk about is Pythagorean triples. So a Pythagorean triple, we know that like 3, 4, 5, those are Pythagorean triples. So those come from knowing that two sides squared equals the hypotenuse squared of a triangle. So I know you've seen a squared plus b squared equals c squared in previous classes. So that's called the Pythagorean Theorem. And the Pythagorean Theorem, there are special side lengths that we know right away. So like 3 squared plus 4 squared equals 5 squared. That's always true because that's 9 plus 16. And that equals 25. And we know that if we have a triangle with two side lengths, we automatically know the third. So if we have a 3 and a 4, and we're trying to find this side, we know that has to be 5 automatically because that is a Pythagorean triple. All right, so when it's talking about Pythagorean triples, I just want you to be aware that we are referring to Pythagorean Theorem as well. All right, so it says to verify the identity, show that each side simplifies to the same expression. All right, so they've got the left side here. All right, and then they've got, that's going to simplify. So they're going to do the first term squared, and then twice AB, which is twice the middle terms, and then the last term squared. So that comes from the previous identity. It's just set up with different variables with exponents. All right, so when you simplify that, a power to a power, you multiply. Here you bring this down, and again, a power to a power, you multiply. So the first one can be rewritten as this, with no parentheses, just written out. So this is simplified. All right, the second part, we've got this term squared plus this term squared. So this is a binomial squared. So again, it's going to be using that same property. So we're going to square the first term minus 2 times the middle terms, and then square the last term. And then the last one, you're going to square 2, and then x squared and y squared. So that comes from squaring everything inside the parentheses here. That's where this part comes from. All right, then again, just going to combine like terms. And when you look, these two are equal or equivalent, okay? So that means that let's see if I can write up here. All right, I don't know why my pen stops writing from time to time, but it does. All right, so this would be your c squared equals, and this would be your 2 side squares. All right, so what I want you to see is that this is the Pythagorean theorem, just a more complicated version than this. All right, so that's what we're looking at with the polynomial identity here. So just be aware of that. All right, so it says, how is the known identity used in the steps here? All right, so that's exactly what we were looking at above. So if a plus b quantity squared, now we're looking at this example, we've got a plus b quantity squared. So a plus b squared, a plus b squared. So a in this case is x squared and b is y squared. So again, this is the same format, just different variables with a higher exponent. All right, so the identity was used with a equal to x squared and b equal to y squared. Both sides of the equation simplify to the same thing, so the equation is an identity. To find a Pythagorean triple using 5 and 4 for your x and y, note that the identity has the form c squared equals a squared plus b squared, where a is this and b is this and c is this, kind of like what I showed you up above. Find the values of a, b, and c when x is 5 and y is 4. So we know it's a 3, 4, 5, but we can multiply those to make bigger varieties of those. So anyways, if we plug in 5 and 4 for our x and our y, then for a we get 9. If we plug in 5 and 4 here, so 2 times 5 times 4, we get b. And if we plug 5 and 4 in here, we get c. So 9, 40, and 41 is a Pythagorean triple. So if you do 9 squared plus 40 squared, that should equal 41 squared. Remember, 2 side lengths are shorter than your hypotenuse. Hypotenuse is always the longest side. So how can you check if this is a Pythagorean triple? Just like what I just said, do 9 squared plus 40 squared and see if that equals 41 squared. And it does, so that is a Pythagorean triple. If you have any questions about the identities, please let me know.